Let's look at this homework problem. In this problem, we're told that a skeeter bug was observed on the surface of a pond. And the student that watched the skeeter bug gave us these notes. Now, we know that the skeeter bug started from rest at point A, and we also know that the skeeter bug stayed on that path. What we don't know was whether the student understands physics. Okay, we think that maybe the student made some mistakes. Now, we don't know what the bug was doing at any point during the travel. The bug could have sped up, slowed down, cruise control, but we know that it stays on the path. So we're not asking, is this right, what the student drew, but could it be right? Is it possible that these vectors describe the motion of that skeeter bug? Let's look at that first point. If the bug starts from rest, then by definition the velocity is 0 at A, by definition. Now the question is, what direction should the acceleration vector point? Now that's the whole topic of problem 3 and 4 in your tutorial homework. It's trying to develop that idea of what does your acceleration look like when you start from rest. Now remember, there's 3 flavors of acceleration: speeding up, slowing down, and changing direction or turning. If I'm starting from rest, if I'm taking that first step, can I be slowing down? You can't slow down from stopped, people. That's as slow as it goes. Okay? Can I change my direction? What if I'm on a curved path? Am I changing my direction? Technically, no. If you start with 0 velocity, you don't have a direction to change. And so that means on that first step, all you're doing is speeding up. And that means that your acceleration vector has to be along the path, in the direction of the next velocity. And so that means that this vector at A is correct. It's got to be tangent to the curve. Okay? So I get yes for both of those. Now, what about that velocity vector right there? Is that wrong or sick and wrong? Sick and wrong. The velocity vector is always out the front windshield. It's in the direction you're going. If this bug is following that path, I've got to have a velocity vector that's tangent to the path. So that velocity vector is wrong. What about this acceleration vector? Could it be right? No. If I look at this as a car, the car's going that way, would this vector make the car turn right or left? Yeah, it's going to turn to the right if that's the acceleration vector. But this bug turns to the left. If I'm looking down on this as a racetrack, the bug's turning to the left. And so that means that acceleration is wrong. I've got to have something towards the inside of the curvature. Now it doesn't have to be that direction. That direction indicates that the bug was speeding up there. We don't know what the bug was really doing. I could have had 90 degrees up there if it was cruise control, or greater than 90 back like this if it was slowing down. Any of those would be acceptable. But it has to be on the left side of the track, into the curvature. Now, what about that velocity vector at C? Is that good? That's good. Now what about that acceleration there? That's 90 degrees. 90 degrees is cruise control. That's okay, right? No. 90 degrees is cruise control and turning. Is that bug turning? No, that's a straight track. And so this acceleration is impossible. That would make the bug turn to the right. The bug can't stay on the path if it turns to the right. So I can either have something in the same direction or the opposite direction or 0. Those would be my 3 choices. If the bug's speeding up, it would be the same as the velocity, the same direction. If it's slowing down, opposite. If it's got cruise control, it would be 0 acceleration, because it's not speeding up, not slowing down, and not turning. Okay, let's look at this point D. Is that velocity vector okay? It's tangent, so it's okay. Now, the student said that the acceleration of the bug is 0. No acceleration. Can the bug turn that corner with no acceleration? No. If you're turning, you're accelerating. And so there has to be some acceleration towards the inside of the curvature. I've indicated one that suggests the bug is speeding up. I could also have had one that was 90 degrees this way, this way. That would be cruise control. I could have had greater than 90 degrees up that way, which would be slowing down. Now if I look at E, that velocity vector looks wrong. It's got to be tangent. But if I correct the velocity vector, is this a possible acceleration?
Yes.
Yeah. It means the bug was speeding up there. I don't know what the bug really was doing, but that's possible. And so the answer is yes. Now, we are told in the problem that the student got these vectors right, correct. What's the bug doing there? Slowing down and turning right. Okay? Slowing down and turning right. Good. Okay. Now you've noticed, if you've looked at the sample exams, that every single sample exam has one of these two-dimensional acceleration problems, where you have to give the direction of the acceleration relative to the velocity vector. Okay? Now, really quick. Let's look at this problem where the kid was on the swing. Now, the velocity vectors are the direction you're going, and the kid speeds up as he goes downhill. He slows down as he goes uphill. And so that means the fastest speed is going to be right here at the bottom. So that's going to be the fastest velocity vector. I'm going to have slower here, slower there, and these are the turnaround points here. Now, if I look at this point B, that's a velocity vector. What flavors of acceleration do we have at B? They're speeding up, slowing down, and turning. Is it speeding up at B? Yep. Yes. Is it slowing down? You can't speed up and slow down, so no. Is it turning? It's on a curved path. So in order to speed up, I need an acceleration that's in the same direction. That's not helpful. An acceleration in the same direction as the velocity. And in order to turn, in this case turn to the left, I would need an acceleration perpendicular. That's going to give me a total acceleration that is less than 90 degrees with respect to velocity. If I look at this point D, at that point we are slowing down and turning left. That's going to give me a total acceleration that's going to be greater than 90 degrees. If I look at this point here, I'm not speeding up, I'm not slowing down. I was speeding up, I will be slowing down, but this is a transition point. All I'm doing here is turning left. I'm still on a curved path. So the acceleration would point 90 degrees. Now these points where you start and stop, since this is the first step and this is the last step, they have to be, you'll learn this in problems 3 and 4 of the tutorial homework, they have to be tangent to the curve. Tangent to the curve. So that's the correct answer to that problem there. Okay, let's look at this tutorial homework problem. This is on the last page of the tutorial homework. You have an object that's going around an elliptical track. and for some reason that you're not told, the acceleration vector of the object always points towards the red dot. Now, this would be the case of something that was orbiting the sun, say. This would be true of the Enterprise as it was coming back in with the whales in what could be argued as the worst of all the Star Trek movies. Anyway, be that as it may, the first question is just, can you draw all the acceleration directions? Well, they told you they point towards the red dot. That's not hard, okay? Now it gets harder when we are asked about the velocity. The velocity is tangent to the path. But the question that makes it difficult is, how long should I draw those vectors? If I assume that this vector is the correct length, how long should I draw the vector at B? Should I draw it the same length, longer, or shorter? What do you think? Longer. Now the question that you need to ask yourself is, what's happening between points A and B? Any point in between A and B is going to have an acceleration vector less than 90 with respect to the velocity vector. So I'm speeding up, speeding up, speeding up, speeding up, speeding up. It's going to be longer. Okay? Now, here's the big question. What happens, how would I draw it at C? Compared to B, would it be longer than B, equal to B, or shorter than B? So think about that, and we're going to use our clicker to answer that question. You can always wash my hands. Okay, with your clicker, people. The magnitude of the vector in C is greater than, less than, or equal to the magnitude of the vector at B. Should I draw C longer, shorter, or the same as B? Really quick. Okay, last call. Whoa, we don't know. We really don't know. Now, folks, at C, the angle is 90 degrees, indicating at C, it is not speeding up, it is not slowing down. However, that's not important. What's important is what's been happening all the time from B to C. All afternoon it was going from B to C. What was it doing during that time? Any point that I choose between B and C has an angle between those vectors less than 90 degrees. That means speeding up. So if it's going 100 miles an hour here, and it's speeding up, 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 oh, right there I take my foot off the gas. Is my vector here going to be longer than B or the same as B? Longer. That's going to be the longest vector right there. The longest vector. Now, we said that 90 degrees was cruise control. Well, generally yes. But there's also this other case of a transition point. That's the point, that's the time when you took your foot off the gas and you're headed for the brake. Everything before this we were speeding up, everything after we're slowing down. Now you'll notice there are 4 transition points in this problem. This is a transition point, that's 90 degrees. This is a transition point, that's 90 degrees. This is a transition point, that's 90 degrees. And this is a transition point. So this object was speeding up till it got to C. It slows down till it gets to E. It speeds up until it gets to F. And it slows down till it gets to A. Check that your neighbor followed that, please.